So the kinds of functions that we're going to look at as the best candidates for representing the algebra in the rational tangle group are a set of functions called Mobius transformations. And a Mobius transformation is nothing more than what we get if I take a linear function, f of x equals ax plus b, and another linear function, f of x equals cx plus d, and I just form the quotient of the former by the latter. So Mobius transformations are just a linear function divided by a linear function. And that's all there is to it. We're going to think of the domain and the codomain for these functions as the real numbers, but there's no reason we should be restricted to the real numbers. You can use Mobius transformations to study the complex plane. You can also convince yourself that if all of these constants a, b, c, and d are rational numbers, then the function f of x is also going to produce rational numbers as its codomain, right? And so that's actually going to be where we play ball with this. We're going to think of x, a, b, c, and d. We're going to think of them all as being rational numbers. So that if you feed a rational number into this function, it's going to spit a rational number out. And those rational numbers, we hope, are going to be the ones which define the fraction of a rational tangle. That's why they call them rational tangles, it turns out, in the first place. And so the first thing I want to do is just ask, what do Mobius transformations do when they interact with one another? This is the important connection that we're going to make that's going to get us out of matrix land and into function land for today. So what I want to do is put the focus in the beginning on the operation that's going to be a part of our group of functions, and it's the operation of composition of functions, where I feed the output of one function into the input of the next. So to see how Mobius transformations interact, imagine that I have two of them. F of x defined by the constants a, b, c, and d, g of x defined by the constants a prime, b prime, c prime, and d prime. And let's suppose that I just compose these two together, and I do f of g of x. Right? So the operation in my group is going to be thought of as composition. Right? F circle g, right, is what I get when I stick these two things together. Let's just do the awful computation. I'll do this one so that you don't have to, of what we get when we compose these two functions together. So I'm taking g of x and I'm plugging it into the input of f. So I'm going to get a times g of x plus b over c times g of x plus d. Right? And then I'll just substitute in for g of x the expression that defines g of x from over here. So in place of g of x, we'll have a prime x plus b prime over c prime x plus d prime. I'll put that in both places. A prime x plus b prime over c prime x plus d prime. And so now I have this hideous looking compound fraction that we want to do something with. So this is one of these classic examples that when you assign it to your algebra students, they all revolt, and rightly so, I think. But we'll muddle our way through this, and the easiest way to muddle through it is to multiply the numerator and denominator of my giant compound fraction by the denominator of this piece that's on the inside, c prime x plus d prime. If I multiply top and bottom by that, c prime x plus d prime, I'm going to get the first term in my numerator is going to be a times a prime x plus b prime, plus b, quantity, c prime x plus d prime. Downstairs, I'm going to get c times a prime x plus b prime, plus d times c prime x plus d prime. Yuck. All right, so this is looking a little better because now we don't have a compound fraction anymore. And so what I want to do now is I want to, in the numerator and denominator, collect all the terms that have an x in them, and then all the terms that don't have an x in them. Right, so we'll just do that algebra to get all the terms with the x's in them. So in the top, the x terms are a prime and b c prime. So we'll collect all of those up to the front. A prime plus b c prime times x. And then the terms that didn't have an x in them would be a b prime plus, let's see, b d prime. So this is going to look nastier before it looks nicer. I promise that I'm going somewhere with this. This is one of those things where you just have to sort of grind out the computation and have faith that it's going to mean something in the end. The x's in the denominator have the coefficient a prime c plus c prime d, a prime c plus c prime d. A prime c plus c prime d x. And then the constant coefficients would be b prime c plus d prime d. All right, so I did all that algebra. I've got all the x pieces where I want them. I've got all the non-x pieces where I want them. And so what you're meant to notice, and this is the genius of Mobius transformations, what we're meant to notice is that if I just look at the coefficients of the x and the constant, and I just sort of take them out of this context, and I just sort of put them into a little array here. A prime plus b c prime, a prime c plus c prime d, a b prime plus b d prime, and then b prime c plus d prime d. This is sort of meant to look familiar. In fact, it's meant to look exactly like, because it is exactly, the result of multiplying the matrix ABCD by the matrix A prime, B prime, C prime, D prime. You should probably check my algebra on that, not now, but later, if you are having trouble falling asleep tonight, which, you know, it's the week of the 2020 election, so we're all having trouble falling asleep at night these days. Maybe checking this computation will help you. But this is supposed to be really good news, right? It's supposed to be really good news because we have functions that when I compose them together with one another, when I plug the output of one into the input of the other, the result that I get is exactly the same result as if I had multiplied these two matrices together. Anytime we can trade nasty function operations for friendly matrix operations, that's a good trade to make. And so that's the big takeaway here. That's how we are getting sort of from matrix land into function land, is that we're not completely leaving all the structure behind. We're going to restrict our attention to functions which are defined by Mobius transformations, because they interact the same way that 2x2 matrices do. And 2x2 matrices are quite friendly indeed. So what are we hoping to do with all of this information? Well, what I'm hoping that we'll do with it is the following. In the first half of this activity, what we're going to try to do is explore Mobius transformations a little bit to figure out if we can find some Mobius transformations that behave, they interact with one another in the same way that the generators of the rational tangle group do. Remember what made the generators for the rational tangle group tick, right? We had a twist and a rotation, a T and an R. And the relations that those satisfied, there were only really two of them. The first relation said that the rotation of rational tangles is an order 2 operation. This was a big surprise when we were first doing rational tangles, because each rotation was nominally just 90 degrees. There was a quarter turn. But it turned out that for rational tangles, 2 quarter turns, or 180 degree turn, actually gave us the same tangle as an original, even if we would have thought in the first place that it should be 360 degrees that we need to rotate. But the R, the rotation element in the rational tangle group, turns out to have order 2. So we have the relation R squared is equal to the identity, right? R composed with R. Then we also figured out that the element TR, so if I did a twist and then I did a rotation, that if I do that process 3 times in succession, I get back to the identity. Right? So these were the relations that define the rational tangle group. We had a generator R, which was a rotation that had order 2. And we had a generator T, the twist, that was an infinite order element. I can keep twisting and twisting and twisting in my rational tangle and never get back to the identity. But if I do twist followed by rotation, that element, TR in parentheses, if I do that 3 times in a row, I get back to the identity. So those were my relations that I wanted my rational tangle group alphabet to satisfy. So we're looking today for Mobius transformations that also satisfy these relations, with the hope that those transformations, those functions, can be used to represent the rational tangle generators. This is the same thing we did last week with braids, right? We have these braid algebraic weird things, and we're trying to capture their behavior with matrices. This week we have the rational tangle generators, which are weird. We're trying to capture their behavior using functions and function composition. So this turns out to be a really interesting question, because what we're going to do in the first phase of this activity is try and focus on these relations, right? R squared is equal to the identity, and TR cubed is equal to the identity. What we're looking for are functions, invertible functions of rational numbers. We're looking for functions that under composition of functions are going to have the same algebra associated with them. So, for example, the first thing I might want to know is, how do these functions under composition actually form a group in the first place? In order to form a group in the first place, we have to have closure, right? The composition of two of my functions has to give me another one of my same type of functions. And because Mobius transformations can be represented by 2x2 matrix multiplication, it doesn't take too much to convince ourselves that if I multiply a 2x2 matrix by another 2x2 matrix, I'm going to get another 2x2 matrix. And so when I compose a Mobius transformation with another Mobius transformation, I'm going to get another Mobius transformation. I'm not telling the complete story here, because there's one more thing we need to do to make sure that my Mobius transformations are invertible. You're going to discover that as part of the activity. But that will be true. We'll have closure for that reason. We also need an identity. So the first thing you'll do is discover what would an appropriate identity function in my Mobius function land be. And it turns out that it's the friendly function e of x is equal to x. The function where whatever input you give it, it just spits out that same input as its output. It doesn't do anything to what you feed it. And so the graph of the identity function is the diagonal line y equals x. Right? So that's my identity function. It's playing the role of the identity element in my group. And then with that in mind, what we're looking for when we're trying to satisfy these relations are square roots of the identity. I'm looking for a function which, when I compose it with itself, is going to give me the identity function, e of x equals x. So that's already an interesting algebraic question. How do I find a function which, when I apply that function to itself, the result gives me the identity function? And then we're also going to be looking for a cubed root of the identity, a function which, when I compose it with itself twice, f of x, needs to give me the identity function. Right? These are very difficult algebraic problems that really didn't get a fair shake in Mathland until sometime in the 19th century. This was studied by a mathematician whose name is escaping me at the moment. It starts with a B. But he studied this question about what are called functional square roots and functional cubed roots. A function which, when I compose it with itself twice or compose it with itself 3 times, gives me the identity function back. Okay? But that's what we're going to be searching for in this activity. What the Desmos worksheet is showing me, first of all, is it's showing me a graph of the Mobius transformation, f of x equals ax plus b divided by cx plus d, and I can change the values of a, b, c, and d to be whatever I want them to be. Right? If I change the value of a, change the value of b, change the value of c. So now you're noticing that the kinds of transformations that we can get are, not all look like straight lines. They look like rational functions, because they are. They're rational functions, linear function divided by linear function, right? And so if I take this version, which for these parameter values, this would be f of x equals 2x minus 3 divided by 2x plus 2. Right? So that's what these values of a, b, c, and d are telling me. That's the formula for this f of x. Then what this Desmos worksheet lets me do is show me the graph of that function composed with itself. And it looks like that function, when I compose it with itself, it looks like it's lying right on top of that diagonal line. That doesn't seem right somehow. But if it did lie directly on top of that diagonal line, then this function would be a functional square root of the identity function. That's weird. Why does it look like it's all on top of the same thing? But what we're seeing here is that the blue graph is a graph of the red function, my original Mobius function, composed with itself once. And in this example, this Mobius transformation, 2x minus 5 divided by 2x minus 4, is not a functional square root of the identity, because its functional square, composed with itself, is not the identity function. But some Mobius transformations, so here's an example of one, 2x minus 5 over 2x minus 2, that is a functional square root of the identity, because when I compose it with itself, the function that I get is the identity function e of x equals x, right? Its graph lies directly on top of that diagonal line, y equals x, right? So this is an example of a functional square root. So you can use f of x to do that part, and f of x to do the functional cube root, right? So here's a Mobius transformation in red, 4x minus 5 over 2x minus 2, which is not a functional cubed root of the identity function. But there are others. If I vary my parameter values again a little bit more. Oh, this one's a little bit harder to do. Trying to get that green function to be exactly the y equals x line. But that's the sort of, oops, oh boy. And so there are some examples where we can find f of x actually is the identity function, once again. So I have a functional cubed root of the identity. In this example, f of x equals x plus 1 divided by negative 3x plus 1. You can check that if I evaluate that, if I compose it with itself 3 times, I get the identity function. So we're going to use this as a tool to help us discover some functions which we hope can stand in for the generators of the rational tangle group, because we hope that they satisfy those same functional identities. When I compose it with itself twice, I get the identity. When I compose it with itself 3 times, I get the identity. And so those are going to be my candidates for what might stand in for the place of R and TR, respectively. Right? Anything which is a functional square root of the identity function might be able to represent the rotation, and anything which is a functional cubed root of the identity function might be able to represent TR. Right? So that's how we're going to take our next steps forward using that Desmos worksheet.